Yes, Debushmita, please continue.
Yes. So Shesha Raghunathan joined IBM in 2011 as part of Electronic Design Automation Timing Analysis Development Team. He has worked on various aspects of analysis, including noise, timing abstraction, and reporting. He later focused on EDA 3.0, analytics in EDA, and ML in EDA efforts and lead time triage efforts. Since 2018, he has additional responsibility of being an IBM Quantum Ambassador, now a distinguished ambassador plus technical ambassador, and is Asia Pacific Geo lead for the program. Recently, Shesha joined as senior research scientist in IBM Quantum and is responsible to drive development of strategic partnerships and in developing IBM's quantum business. Shesha got his PhD in electrical engineering, quantum computing from the University of Southern California, Los Angeles in 2010. So now we can start the session.
All right. Thanks, Debushmita. Thanks, Ritojit. First of all, thanks for organizing the Fall Fest. Appreciate all the time and effort that you guys are putting together. And I'm fairly certain that Kolkata would respond to this in a very positive manner. And I'm sure there will be a lot of excitement in this particular program. And I also hope folks who are participating will also take this forward, take the journey in quantum, and in the short term, immediate future, will also participate in the hackathon. So my best wishes to all of them who have started the journey and who I hope will carry on with this journey. Now, today, I'm going to give a brief overview of some elements. There are many aspects of quantum. A deeper dive could mean anything. There are so many elements to be talked about. But today, we're going to talk about some specific set of things. Just to highlight that's probably a step forward from what you learned from yesterday, and also to highlight some of the value proposition of quantum. But before I do that, let me do a quick recap, just a quick summary of what you perhaps would have learned yesterday. So the key elements, in fact, these are postulates of quantum mechanics. Since quantum computing is based on quantum mechanics or quantum physics, the starting point of any compute are the principles or the postulates therein. Just to summarize the key postulates, first is the state space. You learned that state space is defined by a Hilbert space. The state lives in a Hilbert space. The evolution of a state is defined by the Schrodinger equation. The evolution are unitary transformations. The data that we get out in the real world are through what are called as quantum measurements. That changes the quantum state into a classical bit string that we can consume. And as you add more and more state, the state space, the way it expands is as a tensor product in the Hilbert space. These are the basic postulates of quantum mechanics that also follow through to quantum computing as well. But what is new insofar as the computing paradigm goes? What is new in quantum computing that is not there insofar as compute goes? I'm limiting myself to the paradigm of computation. Now, in classical computation, as you know, it's a binary Boolean algebra that we follow. And the calculations are done through the Boolean algebra. The rules are specified by the Boolean algebra. Whatever that you defined in the higher level language, eventually when you run it in hardware, it is through Boolean algebra. The three new principles that are different insofar as computing per se goes are superposition, interference, and entanglement. The reason why I'm emphasizing computing is because some principle, like say superposition, like say interference, are seen in real world in different ways. Not necessarily in the computing paradigm, but in other paradigm. For example, in the interference, you would have seen the waves in an ocean interfering with one another. And then you could see that the crests and troughs forming because of it being in resonant, in aligned, it goes to a crest. If it's anti-aligned, it's going to go into a trough. These elements are seen in physical reality and physical world. These are not specifically quantum mechanical insofar as phenomenon goes. However, insofar as computing goes, these are not leveraged in classical computing. These three elements play a role in computing. The third, however, entanglement, is fundamentally different. And this is fundamentally different because this is not seen in a classical world. This phenomenon comes only because of the rules of quantum mechanics, and this makes it fundamentally different from classical. And the presence of entanglement also is an affirmation of quantum mechanics and quantum mechanical principle. So on the bottom right, what I have shown is a general two-qubit state. Entanglement requires at least two qubits. So the smallest that you could get is a two-qubit entanglement. So a general state could be represented as in equation 1 here. Uh, this particular state may or may not be entangled. So for example, you can look at equation 2. You may ask yourself, is this entangled or not? So the entanglement as a principle is if I can reduce a particular state as a product of the individual states, then it is said to be entangled. If you look at equation 3, for example, I can tell you upfront that these states are not reducible to a product of individual states. In the state 2 or equation 2, uh, hold on one second. Equation 2, however, let me turn off the video. Okay, equation 2, however, you can see that the state 0 is common between both the sides. So you can pull out the state 0 in the first qubit, and that could factor out, and then you can see that it will be a product of state 0 and a superposition of 0 and 1 on state 2. The third equation, however, you cannot do such a factoring. So therefore, you can see that not all general states need to be entangled. However, the existence of entanglement, however, is there, and they are represented in the general state as well. In general, general state uh, could include entangled state. In general, the general representation, we say it as an entangled state in sometimes in the loose parlance, but really the point being made is there are entangled states there. Insofar as two qubit goes, these are the four qubits, four maximally entangled states possible. By maximal, it is meant equal possible of all of them. There are many, many more entangled states, as you can very well see, if the maximality condition is not restricted. But insofar as maximal entangled state goes, these are the four known entangled states, and these are, later we will learn, these are called as Bell states. Okay, now let's quickly look at what is the application of quantum that sort of motivates what could quantum do. So to that end, I'm going to talk about superdense coding. So what is the problem? So here we have Alice and Bob. They are two entities. The question that is being asked is if Alice can send one qubit to Bob, can we transmit two classical bits of information across to Bob? Is that possible at all or not? That's the statement. So Alice is allowed to communicate only one qubit. There are two bits that it has, and it won't be able to transmit that in that one qubit in some form. So if you look at it, so the path is, let's assume that the initial state, the state that we prepare for Alice and Bob is the maximally entangled state. In this case, one of the maximally entangled states, the plus entangled state. Here, the representation is the first element goes to Alice and the second goes to Bob. That's the usual notation. So you have the entangled state. The one qubit goes to Alice, the second qubit goes to Bob. Okay, so that's what is represented by this. They get one qubit each from this entangled state. Then let's quickly, I'll make a quick comment on one notation in terms of Bell states. I commented on this before, but I'll repeat that again because that is very relevant to this particular protocol. So if you have a two qubit system, these are the four maximally entangled states that are available in the two qubit system. So you have 0, 0 plus 1, 0, 0 minus 1, 0, 1 plus 1, 0, and 0, 1 minus 1, 0. What is interesting about these maximally entangled states is that they are orthogonal or in fact orthonormal to one another, which means that they could form a basis for a particular two-qubit system. So that is, in other words, what it means is that you can form a measurement operator to measure each of these states. So you have, think of it as orthogonal vectors in this high dimensional space where you can measure each of these in that particular dimension. So if you do get a 0, 0 plus 1, 1 state and you measure it in this basis, then you will get the first equation. So if you measure it with the first measurement operator, you will get 1 in that particular and 0 in all others. And similarly, if you have 0, 0 minus 1 and you want to measure that, you're going to get 1 in the second equation and so on and so forth. So these are known as what is called as a Bell basis. And you can measure these in these particular bases. So typically we measure in what is called as Z basis. But in order to measure in this basis, all you have to do is apply some unitary and rotate it into a basis that you can measure these in their respective basis called the Bell basis. Now, why is this important? So what Alice can now do, and Wallace, so let's go back to the statement of the problem. So Alice has 2 bits of classical information. She can transmit 1 qubit across to Bob. What we said as a setup also is that they have an entangled state which they share, Alice and Bob, and they are not, they are physically distant. They are not immediate neighbors or anything. So they get 1 qubit for Alice, the other qubit goes for Bob. Now, can we encode this? So what Alice can do is apply this particular simple formula. Since the initial state, as you know, is 0, 0 plus 1, 1, if it wants to encode 0, 0 as the classical bit of information, it doesn't do anything on its qubit. Remember, what is important is Alice has access only to its qubit, not to Bob's qubit. So if you see the first qubit here, it is identity. So which means psi is same as what it was prior. But if it wants to encode 0, 1 as the information, so it applies a sigma z operation on its qubit. When you do apply that, you get a phase, a relative phase. So it becomes a 0, 0 minus 1, 1 state. If it wants to encode 1, 0, it applies a sigma x operation on it that basically flips 0 and 1. So you get a 1, 0 and 0, 1 state. And if it wants to encode 1, 1, it applies this particular gate, I sigma y, then you get 0, 1 minus 1, 0. So all it's doing is rotating its qubit. And by rotating, what it's doing is it's aligning to one of the 4 basis states that we were seeing. And so when you have that, and it then sends its qubit across to Bob. And now Bob has 2 qubits, and therefore the Bob can now do 2 qubit measurement. The Bob can choose any number of measurement possible, but in this particular case, let's say he chooses the Bell basis as the measurement, which is the basis in which Alice encoded the 2-bit information. Bob can exactly get the bit string out in the order that it was sent. So the math of it is actually fairly straightforward. If you do apply the simple math and you see that the state gets transformed into these particular thing. And since I told you that these are orthonormal, you can actually test it out. If you have the inner product of these or any of these, you will see that they are all 0. And if you inner product of itself, you will get 1. So you will see that these are orthonormal, which means that when you do measure, when you get a 1, you know exactly that it was in this particular state. So when Bob measures in this Bell basis, Bob will be able to recover the 2 bits of information. What is important? So what did we just do? Alice communicated 1 qubit of information, but with that, it could transmit or communicate 2 classical bits of information to Bob. And that's fundamentally very different. You cannot do this kind of transmission in a classical setting, which makes it very unique. This is very unique to quantum because the resource that we have used is an entanglement as a resource. This element of communication, in fact, is one of the basic coding element, and this is developed a lot in what is as a quantum information theory, particularly in the communication setting. This is very actively used, and a lot of research and analysis are built on top of these basic observations. All right, let me pause for any questions. Debashmita, if there are any questions thus far.
Yes. Lakshmi Prasad asks, how does Alice choose which bell state to encode the classical bits?
So, so here is the rule. So let me walk through this again. So Alice wants to transmit, let's assume 00 is the information it wants to encode and send. If it is 00, the rule that Alice applies is it just applies identity on its qubit. If it wants to transmit 01 as the bit across to Bob, then the rule is it will apply sigma z on its qubit. And when you apply sigma z, you just apply the math of it. If you apply sigma z to the first qubit, you will see that there will be a relative phase, because in sigma z, you will have a -1 for when the bit is 1. So you will gain a relative phase. So you can sort of see that when you apply sigma z on Alice's qubit, you will get as -00 -11 state. Similarly, if it wants to transmit 10, the rule it applies is sigma x on its qubit. And if it does apply sigma x, as you know, sigma x flips 0 to 1 and 1 to 0. So the initial state was 00 plus 1, 1. And the first qubit flips, which means it becomes 10 plus 0, 1. And similarly, if you apply I sigma y, and if Alice wants to transmit 1, 1, it applies I sigma y. And when you do, just apply it on the 00 plus 1, 1 state, you will get 0, 1 minus 1, 0 state. And that's how it encodes the information onto this quantum state.
So there is one more question, that if I want to transmit 00 using 00 minus 11 entangled state, is it possible?
Maybe they would want to explain. I guess you can always. I mean, it's up to Alice to choose. Like you can always set 00 as I sigma y. There is nothing stopping Alice from doing any of these things. These are arbitrary mapping, right? There is no direct mapping, one-to-one mapping as such. As long as it is understood what the encoding mechanism is, so that when Bob measures and gets the results and sees the state, Bob then knows what to interpret. If Bob needs to interpret 0, 1 minus 1, 0 as 0, 0, might as well. So there is no one-to-one mapping per se. Any technique is as good as any other. There is no one-to-one mapping per se. So since there is no information that we directly encode from the classical bit onto this, it doesn't matter how you set this up.
There is one more question, that can we say that the information content of a qubit is much higher than the classical bit?
Communication wise, yes, not information content than classical bit. One bit is one bit of information. There is nothing more. What I mean is when you communicate, there is more classical information that you can carry on a quantum qubit. And that's what this one is showing. It's clearly showing that it could communicate two classical bits of information from when Alice sends just one qubit across to Bob, it's carrying two qubits of information across. And that's how you would want to interpret it.
So there is, I think, one more question, and are these operations on respective qubits of Alice unique corresponding to the classical bits?
As I said, there is nothing unique about it. For example, you could just flip all. So, for example, you could have chosen I sigma y to encode 00 as information. So the key element is the key observation that you need to note is when you have two binary digits, two binary bits, there are four combinations possible: 00, 01, 10, 11. These are the only four possible combinations possible in a binary system. Now in Bell state, we learned that there are 4 orthogonal bases available. So mapping which specific combination of bits to what is really arbitrary. It doesn't matter. So since it doesn't matter, we can choose one, which is what is shown here. So how it is mapping. So when you have the encoding, obviously there is a corresponding decoding, and decoding here is not explicit, rather it is inferred. When Bob measures in the Bell basis, there is an implicit inference that the plus state or 0, 0 plus 1 corresponds to 0, 0, which is not explicitly shown in this picture, but there is certain inferencing or decoding that is happening post measurement, what that state corresponds to. So as long as that Alice externally outside of this thing communicates that this is the encoding that I'm using, then Bob can certainly infer the string in any which order that Alice sends.
And Shongita is asking, does superdense coding violate no cloning protocol?
No, certainly not. There is nowhere can you see that the bits were cloned. All it did was it rotated the system. So note that all these I, sigma Z, I, sigma X, I, sigma Y, I, these are all unitary operations. When you perform a unitary operation, you cannot clone. Clone means that you have one qubit and you take, and that state exactly is copied over to the other 2 qubit. You make 2 copies of it. There's no way that a unitary transformation can do. A reversible operation like unitary transformation cannot do that kind of a copy. So it's a simple proof that you can actually look up, and I'm sure this was covered as well. So the point to note is these transformations are all unitary transformations. So certainly there is no cloning theorem violation. No cloning theorem violation has not happened, and there is no cloning happening here.
Okay, I think we can continue. There are no more questions.
Okay, great. So let's quickly go to the next part. So first, I'm going to go a little bit into the state representation. Today, we're going to cover generalize the state representation. Remember in the postulate, I mentioned the state as a fundamental element. I guess in yesterday's lecture, you would have seen this state representation. A general single qubit representation is shown by this, where psi is equal to alpha 0 plus beta 1. The key part here is mod alpha square plus mod beta square is 1, where alpha square and beta, mod alpha square and mod beta square represent the probability of being in 0 and 1 respectively. So this you would have seen in yesterday's lecture. This comes purely out of, in the quantum physics side of things, this comes purely from the Schrodinger equation, where the Hamiltonian evolution corresponds to a unitary evolution, and our state there honors this rule. Right? So that this is a pure state. When you say pure state, naturally you start to think, okay, is there something that is not a pure state? So here, there are 2 aspects that you would want to think about. Today, we're going to cover one of them. I'll touch on the second one a bit, but the first one is what we're going to focus on primarily today. There are 2 limitations of the representation insofar as state representation goes. One is ensemble of pure states. So by ensemble of pure states, what is meant is if I have multiple pure states in a system, think of state preparation, for example. Let's say we always assume the initial state is 0. That need not be the case in many cases. Physically, some states could be 1 and 0 with certain probability. Then what you are getting actually is that with certain probability, with a very high probability, you're going to get a 0, but with a non-zero probability, you're going to get a 1, 2. There are many, many such scenarios where you have this kind of ensemble, where you have certain probability of being in certain pure states. Now, the question then is, how do you represent that? That cannot be captured in the pure state. I'm going to elaborate on that particular point subsequently. So that's one limitation of the pure state representation. The other, and this will be elaborated in a couple of days from now, is noisy system or an open system. So typically, in the example that you have, I've shown the typical cavity QED type of a setup. Imagine that you have an atom, a two-level atom inside a cavity, where this cavity, think of them as two reflecting mirrors, and a light can reside in here. That's the cavity mode. And then there is a two-state system, 0 and 1. They can have interact with one another, 0 going to 1, 1 coming to 0. That's the Hamiltonian connecting 0 and 1. And there will be a Hamiltonian connecting the matter and the light, which is the coupling Hamiltonian here. The color in green indicates that these are Hamiltonian, which means these are unitary. So the system like cavity QED type setup will have a Hamiltonian that connects the physical states of matter and light together, and this essentially captures the key elements or the evolution of that particular system. So the physics is all about, can I, given the state today, now can I predict what will be the state certain time later? And that description is provided by this evolution. Open system, however, is when, so for example, you have a spontaneous emission. So typically a high energy state may emit a photon and drop down to one level of energy below. So for example, in this picture in yellow, what is happening, or orange, it emits a photon of frequency based on the energy difference of 0 and 1, and it drops the state of the system, the state of matter drops from 1 to 0, but you get a photon of light out. Now that is not captured in a Hamiltonian. A Hamiltonian is necessarily a unitary, which means that it has to have a probability of 1. If you accumulate all the information, you should be able to exactly say what is the state. But in this case, you are losing information by the photon going away. It spontaneously drops to state 0. And this, in many ways, you guys would have seen in what is called as a decoherence. If you have seen IBM quantum system, the T1 time is the time that a state can reside in 1, and it drops to 0, because that's the law of nature. High level energy invariably tries to find a lower energy or a ground state energy. There is a non-zero probability of 0 going to 1 too. But this is typically true in a high energy system, but in a very low energy system with low temperature, this doesn't happen as much as the other way. Because the way the law of nature is that it always tries to go towards the lower energy system. So these kind of interaction, so here what we imagine is when you pass a photon, it could necessarily be that it could be that the system is interacting with some other element outside, and that's how the energy is getting transmitted. However, you do not have access to things that are outside, so it sort of goes into some ambience here and you lose it. Since your state is described by this element, and this particular interaction is beyond this particular description, these are necessarily a non-unitary. These are not reversible operations. So this description then requires, how do I represent that in the pure state system? You cannot represent that in a pure state system. That's the limitation of the representation, because a pure state necessarily tells you exactly what is the state of the system, which is alpha 0 plus beta 1. So you should be able to go tell exactly. But if you have a spontaneous emission, for example, with a non-zero probability, 1 may become 0, and this interaction then changes the state of the system. So for both these reasons, it is important to note that the state representation, the pure state representation that you may have learned, it's limiting in some sense. Pure state representation, however, are very good in many other ways because it's easier to calculate. But I do want to mention that there are certain limitations. I'm not going to elaborate more on the second part, as I said. I think you have a separate session on the noise part, so you're going to hear a lot more of that. But today I'm going to pick just this. So assume that you have an ensemble of pure states. That is, with certain probability pi, you have a state psi I. How do I represent that? So that's what we're going to see in the rest of the lecture today. So here, so the same thing here, we have psi I with a probability pi. Psi I you can imagine in general as alpha I 0 plus beta I 1. in general. Now, so can I, let's imagine this. So let's say much like how you would have done in classical things, when you have a distribution of various things, you generally say you're going to weight it. So you're going to say with probability P, this is state Pi, let me sum it up, much like how you do the weighting. So if you do that, is that representable? Does it make sense? Is this a good way to represent? But if you take this conversation forward, what this necessarily implies is that you have Pi of alpha I 0 plus beta I 1. Note that alpha and beta are probability amplitudes. These are not probabilities. So you get probability only when you have a mod square of each of them. That's when you get a probability. Or in mathematical terms, probability is an L1 norm and probability amplitude is an L2 norm. You cannot multiply these two. This just will not work. It's like multiply first and square first and then multiply. These are two different things. So you're not going to get the right answers. These distributions will not make sense statistically too. So therefore, as I mentioned, this is a probability and these are probability amplitudes. So you cannot represent a state like this. That would not make sense. So how would we then represent a state which is an ensemble of multiple pure states? So let's go and try this out. So let's assume that you have a state in a general state. I'm not talking, I'm dropping the subscript I for convenience. Let's say psi is alpha 0 plus beta 1. Note that the complex conjugate, the transpose, the adjoint of that state, which is a bra of psi, is alpha star 0 plus beta star 1. So it follows from a simple transformation. Now let's do what is called as an outer product of the two. So you have psi 0, psi, which is the outer product representation. When you do that, a simple linear algebra math of it, you will follow here that it's mod alpha square 0, 0, and you have alpha beta star 0, 1, beta alpha star 1, 0, and beta square of 1, 1. And if you work this out, it's a simple matrix where 0, 0 state corresponds to the top left, 1, 1 state corresponds to the bottom right, and the cross terms are 0, 1 represent the top right and 1, 0 on the bottom left. You see this represented. The diagonals are called the probabilities and the off diagonals are the transition probabilities. So what is, so I do have this representation. I get the math, I get the matrix, which is great. But what does it mean? All it means is you need to check the statistics. Do I get the right statistics or not? So let's say I have a row stand for psi in bracket notation. So I introduce an operator called trace of row, which is basically you add up all the diagonals. So row of JJ represents the diagonal values. So in the previous page, if you can see, the diagonals are, as I mentioned, these are the probabilities, right? So the definition of the trace operator, the TR of this particular thing is you add up all the diagonals. When you do that, you get alpha square plus beta square, which you know by the definition of psi as 1. So you know already that when you have a pure state of alpha 0 plus beta 1, you know that alpha square, mod alpha square plus mod beta square is always 1. And therefore, this trace is also 1. Now, let's measure it. Let's say you did a projective measurement and you did a 0 on it. Trace of 0, 0 of row, you get basically what this one does is it's telling you pick the 0, 0 position of this particular matrix. And you can know that this is mod alpha square. You can also look at it in the outer product representation, which is mod alpha square. So if you're multiplying, you want to pick this one out. So when you do that, you get mod alpha square. And if you want to measure 1, you apply a projective measurement of 1, 1, you get mod beta square. So what is interesting is from quantum mechanical principle, all you have access to is the statistics. So this representation in terms of statistics is identical to the other pure state representation that you had in a vector form. This, however, is in a matrix form, right? However, this honors the statistics of a pure state that you already have. And what is more important, is that all these are probabilities. These are not amplitudes, right? So, and the probabilities that matter are the diagonal terms. And you know that these are all probability values, right? So now, what is now interesting is now let's take this pure states of pi of psi I. And what I've shown in the previous chart is psi, the way it is shown, represents the pure state. And if we generalize that now, take the ensemble, P of psi I is same as Pi of rho I, where rho I is psi I. Now, when you have the ensemble, now you can do a Pi of rho I because in terms of metrics, now they are all probability. You're not violating anything, so they make sense. So if you do that, you have sum of I Pi of rho I, which is nothing but sum of I Pi of psi I. Note that I've not mentioned anything about what different psi-i's are. For all you know, they need not be orthogonal to one another. In general, there is no constraints on what each rho I is. It's just the way you represent it. You could now start playing with it in terms of probability, the way you would do in the classical system. Now let's look at the statistics again. Apply that 0, 0 or the projection to state 0 on the system rho. So just expand rho. As you know, rho is given by this sum of I Pi of psi I. If you apply that, you can know, and trace is a linear operator, so you can take the sum out. So trace can go inside. So it's same as applying a projection onto individual state rho I. So that probability, the trace of what is the total probability of being in state 0 on the state rho, what is this? What is its probability of being in state 0 is basically a summation of I pi times mod alpha I square. The same goes with 1, 1. So if you have and ask the question, what is the probability of it being in 1? You just do the pi of mod beta I square. And that this sort of makes sense because now both of them are probabilities. You can multiply probabilities. On the other case, if you had the other representation, you won't have been able to do certain calculations. So now these statistics will be repeatable and this makes sense in terms of representation. Let me pause for any questions.
So there is no as such question, just one of them, Oyon is asking this outer product that you define, that is basically the density matrix.
Yes, there are many different terms. Density matrix certainly is a more often used terminology. Outer product as such is a terminology coming from linear algebra. In fact, matrix algebra, it has nothing to do with physics per se. But in the physics context, outer product doesn't necessarily is equal to a density matrix, but it is conventionally used a lot in density matrix representation. In fact, a general operator. So note that we are trying to identify a state of a system. Rho represents a state of a system. An operator can also be represented in terms of this outer product because ultimately an operator is also a matrix. Once you have a matrix, you will have elements of the matrix and each element is a position in the matrix, right? Ij in the position, and that Ij is you can always represent that as a outer product and show that. So this outer product is a very generic term. In this example, I'm using it to represent a density matrix, but it could represent an operator too, not necessarily a state of the system. As this notation is coming from a general mathematical linear algebraic setup.
So Shomodip is asking, the trace is independent of basis. Is this the reason for having trace operation in the density matrix?
So trace, in fact, so as I defined, trace is nothing but you add up the diagonal. But in terms of operation, there are many other rules which I'm not covering today. That's beyond the scope of these things. I've not covered it here. I don't want to confuse beyond a point, but simple thing to see is, for example, if I had an operator like here, a trace is defined to be the expectation value of being 0. So you can then trace is defined to be like this. You have you have the zero here on the left, and then this zero becomes on the other. It becomes an expectation value of the state of the initial state row vis-a-vis the projected state of zero that we have. So it's nothing but an expectation value. That's what it represents. There are many mathematical elements given that rho is a matrix. There are properties based on which certain other things follow. Just note that it's equivalent of an expectation value. And second thing is that the trace of rho, the state of the system in this matrix representation adds up in a pure state scenario will add up to 1 because you are adding the diagonal, which is alpha square and beta square. So to that extent, you would want to keep it to that, and note that it's a linear operator. So you can always move the plus, you can take the trace inside and outside and so forth.
Okay, there are no more questions, so I guess you can carry on.
Okay, so hopefully with this, you got a sense of limitation of being in a pure state insofar as vector representation goes. So you do need a matrix representation of the pure state. Note that this is also a pure state, but represented in a matrix form. When I say pure state, I mean, when I said is pure state, so let me just, limitations of pure state, I put quotes on it. That quote is supposed to mean this vector representation of the pure state. So even in density matrix, you can represent this pure state I just showed you. But typically when we say a pure state, we typically mean in this kind of a notation. At least in this context, that's what I mean. All right, now let's quickly go to the next part, and then I'm going to stop there. Unitary evolution. So the two pieces is first we define the state. How does it evolve becomes just as important. So you know from yesterday, you would have learned that as state psi, if you apply a unitary operator on that, the final state is represented by u of psi, u being the unitary operator on the state initial state psi. You can also note that the complex, the adjoint operation is represented by this. Bra of psi is goes from bra of psi to bra of psi of u dagger. And this is the adjoint operation there. Now, if you have row representation, so this shows the evolution in the vector representation, but in the matrix representation, how does it evolve? So this should follow straightforwardly with the above two equation. If you apply unitary operator onto a row, which is u row u dagger, so you have to apply on both sides because of the evolution there is. And when you expand that, you will see that u of psi and bra psi of u dagger. And if you see it, it sort of makes sense. Note that if you apply unitary on a state, initial state psi, you know that the final state is u of psi. If you look at the left of it, it's u of psi. The same in the bra notation would be bra of psi of u dagger, which is on the right. So the final state would be psi, if you want to represent it by psi tilde or something, it's going to be psi tilde of psi tilde. So that again will be a pure state, right? And so the evolution of a density matrix from a pure state on applying a unitary goes to a u row u dagger, and that's the final state of rho, which is, let's assume, a rho prime. It evolves to rho prime. The final rho prime is represented by u row u dagger. Now let's generalize this. So here it was a single state. In general, in an ensemble case, which is what we've been studying thus far, you're going to have a pi of rho I. So it's nothing but summation of I, pi, rho I that I talked about earlier. If you had u row u dagger, which is the evolution, the initial state is rho, the final state is u row u dagger. Let's assume it to be rho tilde. So the final state rho tilde is you apply u onto the ensemble state, which is pi rho I. Since unitary is a linear operation, you can move it inside. So you have pi of ui rho I u dagger. And if you represent by rho I prime, then you know that the final state is pi of rho I prime. So you can see that you have the density matrix where the pure state evolution is represented this way. Now this could be generalized to an ensemble state. where you have pi of rho I. And when you do that, you can also define, or you have mathematical way to calculate the evolution of this ensemble state based on the unitary evolution. It's a straightforward calculation that you can see that it is easily representable in this form. Let me pause for any questions.
No, there are no questions.
All right. In the last few minutes, let me comment on this. So this particular thing, I wanted to make a quick comment on this because of it being topical at this particular point in time. My colleague Dhiraj will talk about the initial thing, superdense coding, the density matrix, how to program it, run it, etc. But this one, I don't think we're going to cover it today insofar as programming goes. But nonetheless, this is very topical. I wanted to mention it here. Just so that you understand this. So note that we did talk about superdense coding and how quantum is different from classical. Here, the Bell's inequality. A little bit of history. 1935, Einstein wrote an important paper where he claimed that quantum mechanics is not complete. And the point that he was trying to make was basically he got an entangled state, actually the Bell state that we saw before, 0, 0 plus 1, 1. And he said that you cannot represent it as a product, and therefore they are not local, and therefore there is a non-locality. He thought of having what is called as a local realism implicit in that particular paper, and then claimed that therefore quantum mechanics is not complete. John Bell in 1964 revisited that particular argument of this and then expanded on that particular thought and said, what can we calculate if you did have entanglement? Now, that's the context to this particular work. So let's imagine that you have Charlie who can build a 2-qubit state, and then Charlie gives 1 qubit each to Alice and Bob. Now, the setup is that Alice and Bob have 2 different measurements that they could do, Q and R. Alice can do Q and R, and let's assume that these measurements results in +1 or -1 as the result. And same goes with S and T that Bob can do. And the other part that was implicit there is that they both do it simultaneously. There is the measurement that Alice and Bob do, they do it simultaneously. There is nothing that could be communicated or anything else. So it all happens simultaneously. Let's assume that. Now, the construct is interesting because if you look at this, QS plus RS plus RT minus QT. If you see this particular equation, what is interesting with this is it refactors into Q plus R times S plus R minus Q times T. Note that the value of Q, R, S, and T are plus or minus 1, as was mentioned before. The way it was set up, the way this is set up, you can note that Q plus R times S is either 0 or the second one is 0. And this is a very simple math. You can replace +1, -1, and so forth. You can try out all combinations. You will see that either one of them is 0. And therefore, the other one will be the net of it you will get the result will always be either +2 or a -2, the way this particular problem is set up. So QS plus RS plus RT minus QT is plus or minus 2. So if you look at the expectation value of this, will always necessarily be less than equal to 2. Okay, so you can work this out. This is a fairly straightforward math. So now this setup, what is implicit here is that this sort of, if local realism is true, then it will necessarily honor this rule because there is no other communication other than the measurement and you get the result. Right? There is nothing else happening here. Now let's assume that Charlie now builds a Bell state as is shown here, 0, 1, -1, 0. Note that it's a maximally entangled state. And let's say the measurement that that Alice does is defined by Q and R, same as before, and S and T by Bob, same as before that we had earlier. But this is the operator. These are the operators that they apply. Now, the bracket notation that you have here, this represents an expectation value, a quantum expectation, as is called. You just do the math. The left angle bracket represents the bra notation of it. So you take the complex conjugate, the transpose of it, transpose and conjugate it. That will be the left. On the right is the regular state. You apply this state, this gate on these state. You will get 1 over square root of 2. And same goes with RS, RT, and QT. You will get a minus 1 over square root of 2. You can just do a simple linear algebra. You should get this answer. What is interesting, however, is if you see the result from the context of local realism, the expectation value of QS plus RS plus RT minus QT, as you know, expectation value is linear, so you can always do expectation and then add them up. If you see the quantum expectation, if you add them up, the same set of equation that we had earlier, you get 2 square root of 2. Earlier, it was limited to 2. If local realism was true, you will be limited by 2. If entangled, the way it is defined is true, you will get 2 square root of 2, which is very different. And what is the implication? Why did I say this is important? This year's Nobel Prize was awarded to folks Aspe, Clauser, and Zeilinger. They did experimentally demonstrate that Bell's inequality was true, and they showed through experiments, they used optical way of doing it. They showed that the 2 square root of 2 that was derived in 1964, they could demonstrate that actually was realizable in experiment, and that indeed was true. And that clearly showed that the local realism assumption that Einstein had made was not necessarily true. And here it honored the quantum mechanics, and that was what was critical there. And that has a far-reaching significance, and that becomes the bedrock of what is now quantum information science. Since this was topical, I thought I should talk about it, at least make a comment on it, so that you get a sense of what this award was about. It is quantum mechanics, confirming quantum mechanics to be true, but this has a big implication to quantum information science, because that inequality is the bedrock of many of the quantum information science theory. Let me pause for any questions.
Yes, so there are a couple of questions. Two questions are quite similar, so I'll try to just pack both of them together. So is it that can we take any other combinations of plus and minus? Why is QT negative, or is this intentionally designed?
It is intentionally designed to bring that up. So the point is that you can try out any combination. So typically when we do research, you constantly play with various things. You set it up in a way that this contradiction should be shown. In mathematics and in many other science, proof by contradiction is one way of doing it. And many a times it's about playing with these terms. There could be, I've not played with this, maybe there are other equivalent representations that will give similar results too. But this is one way that shows that if you have this, you calculate this, you measure this, and this is when they did implement, you can calculate the expectation value of QS, the expectation value of RS, RT minus QT. You can all do this in experiment, and they then show that if it is 2 root 2, then this means that the math behind all of this is correct. So it doesn't matter what exactly you set it up. You could set up any other way, as long as you can show bring out this difference. The key is the difference. Oops. The key is the difference. The classical way, which is this, which you can show that it has to be less than 2, less than equal to 2. And in the quantum way, it will necessarily be 2 root 2. If you can bring that contradiction out and show what does the experiment show, does it show 2 or does it show 2 root 2? And if it shows 2 root 2, that means that local realism is not true. There is entanglement. There is such a thing called entanglement. The math behind all of that is validated.
Okay, and one more question here is that, is the choice of S and T operators unique?
I think I commented on this in brief. I've not played with this a lot. You can give it a try. You can try out other combinations therein. I won't be surprised if there are other similar things, but it's the setup of it, this QS plus RS plus RT minus QT, right? That setup plus the operator that leads you to 2 root 2. And that setup is what together matters. And that clearly shows if you had local realism, you will get only less than equal to 2. If you had entanglement, you will get 2 root 2. That setup is what is important together. Any other
Okay,
questions?
so no, Debosmita, on to you then.
Yes. So now we'll go directly to the hands-on session. First of all, thank you, Shesha, for this wonderful talk. And now we can go to the hands-on session, which will be taken by Dhiraj. And I would like to seek permission from Dhiraj if we can record his session also.
Sure. Yeah.
Yeah, so Dhiraj Madan is an advisory research engineer and IBM Quantum Ambassador at IBM Research India. He works on research problems in quantum computing and machine learning with publications in top international conferences. He has also conducted several tutorial sessions on quantum algorithms, including a lecture at a course on NPTEL. Prior to joining IBM Research, he completed his master's in computer science and engineering from IIT Delhi, where he graduated with an Institute Silver Medal. So, Dhiraj, you can start your session now.
Sure. Yeah, thanks. Let me start. So, so actually, yeah, so Shesha has given a wonderful theoretical overview of these topics on density matrices, like ensemble states, density matrices, and super dense coding. So we'll be looking at the programming parts of some of these. So I'll be sharing some IPython notebooks. Let me share my screen. So these IPython notebooks are taken from basically Qiskit textbook, which you'll find online. And yeah, so let me actually, so basically if you go to this link on Qiskit textbook, you'll see all these notebooks over there. So I'm reusing most of the material from there. So one topic which I wanted to cover before covering today's sessions is also this idea of a block sphere, right? So we have seen a qubit which can be represented as alpha ket 0 plus beta ket 1. Let me actually stop my camera to save bandwidth. Um, just Yeah, yeah. So, okay. So basically the idea is that a qubit can be represented as alpha ket 0 plus beta ket 1. And the idea is that how to now visually understand it, right? How to represent it visually. And the thing is that the idea over here is that we actually map this. So basically it lies in a complex circle in a complex plane on C square. And the idea over there is that since it's difficult to visualize the C square space geometrically, the idea is that we map it to R cube, as in three-dimensional real space, because two-dimensional complex space will actually have four components in one sense, right? So one real and one imaginary for each of the two complex components. So four-dimensional we can't imagine directly. But the thing is that on C square, a circle on a C square, which is SU2, can be isomorphically mapped to a sphere in three dimensions, right? Or SO3. So SU2 is isomorphic to SO3. This is the language which people from representation theory use. And the idea in this sort of a mapping is that if you take a sort of a qubit as alpha 0 plus beta 1, what I first do is that I eliminate the relative phase part and I make both of them. So what I do is that instead first I'll eliminate the global phase and let's assume that alpha is real. Once we do that, then essentially there is just a relative phase which is associated with this beta part, right? And now I can write it as alpha ket 0 plus e to the power iota phi beta ket 1. And here alpha and beta are now both reals and the complex part is captured by the space phi or phi. And since alpha and beta are supposed to be normalized, I can take them to be sine and cosine of some same angle. And typically we take this angle as theta by 2. And now we can represent this qubit as cos theta by 2 ket 0 plus e to the power iota phi sine theta by 2 ket 1. And now you see that we only have two angular components, right? Theta and phi. And phi being a relative phase can run from 0 to 2 pi. Theta by 2, which basically represents positive, like an angle in the first quadrant, because both of these components are positive reals. So theta by 2 represents an angle in the first quadrant, which means that theta overall lies between 0 and pi. Okay. And so now basically what I can do is that I can represent theta and phi as the polar angles, right? So if you're familiar with like in basically if you're familiar with the idea of latitudes and longitudes, so these polar angles are somewhat similar to that, right? So this phase phi, which is called as the azimuthal angle, represents somewhat like a longitude on the sphere, and theta will represent the latitude part. But here typically in our so here typically latitudes, they run from, you have minus 90 to 90 degrees from north to south pole. Here we run them from 0 to pi instead, right? So it will be from 0 to 180 degrees instead of minus 90 to 90, but that's more of a convention. So let's see an example, right? Because the best way to visualize it is through example. Okay, sorry. So I'll have to import some cells. Okay. Yeah. So the thing is that so if you look at the state ket plus, right? So ket plus is nothing but 1 by root 2 ket 0 plus 1 by root 2 ket 1. And if you choose phi to be 0, this angle phi to be 0, so there is no relative phase, and theta to be pi by 2, which means theta by 2 is pi by 4. So cos pi by 4 ket 0 plus sin pi by 4 ket 1, that will give you 1 by root 2 ket 0 plus 1 by root 2 ket 1. And so here we have, so here we will be able to represent it by theta equals pi by 2 and phi equals 0. And theta equal to pi by 2 would mean a vector on the equator, right? Because here from north pole we start at 0 and then equator is at pi by 2. And then there is no relative phase, so it's on x-axis. So this is actually how we'll represent the ket plus on this block sphere. And we can also see it from here, right? And in fact, what you can actually do is that you can actually try multiple different angles. So let's see. So here actually I can, so I can actually, okay, so here this does not allow me, but what I can do is that I can change angles from here itself, right? So suppose let's try to represent ket 0. So ket 0 will be represented by 0, 0 and 1, right? Because the radius is 1 in these spherical coordinates, we are always on the surface of the sphere for pure states. So if theta and phi both happen to be 0, I'll get like, so cos 0 is 1, and so it will just be ket 0. If I make this angle pi, I'll get ket 1. So just try these, and yeah, I'm sure you will be able to try other angles and understand this concept in more detail, right? So any questions about the block sphere part? Because then I'll move on to the next topic, which is the super dense coding.
No, Dhiraj, there are no questions.
Okay. Let me move on to super dense coding. So super dense coding protocol is what Shesha had explained. And just to recapitulate, the idea here is that we are trying to communicate one qubit. So Alice and Bob, they are sharing an EPR pair. And based on the amount of the information which Bob wants to send, he applies some operations. And in the end, by sending his share of the EPR pair, which is just a single qubit, Bob is able to transmit 2 bits of classical information, right? So, okay, so basically, okay, so let's say that Alice is sending the information to Bob. So Alice sends 2 classical bits by sending 1 qubit. And the idea, the protocol, which we just saw, was that they are already sharing an EPR pair. And so actually here in this table, they have omitted this 1 by root 2 factor. So originally it was in the state 1 by root 2 0 0 plus 1 by root 2 1 1. And if Alice wants to send, just 0 0, she does not apply any operation, which means that like she kind of applies identity, and she just sends this as it is. So Bob will receive this original EPR pair. If she wants to indeed send 0 1, then she applies an X gate, And here, if he applies an xk to the first part of the qubit in EPR pair, it will be 1 by root 2 1 0 plus 1 by root 2 0 1. On the other hand, if she wants to send 1 0, then she'll basically apply a z gate. So z gate will have a minus sign on this 1 1 part, and if she wants to send 1 1 1, she'll apply both z and x, and she'll end up sending this state minus get 1 0 plus get 0 1. And Bob, on the other hand, who does not have knowledge of the actual classical bits, applies an unentangling operations, and he is able to recover 0 0 0 1 1 0 and 1 1. So let's see an implementation of this in Qiskit. So first of all, let's create an EPR pair. So we have a quantum circuit. We apply the Hadamard gate to, so the qubits are indexed 0 and 1. So we apply Hadamard gate to qubit 1, and then we apply a C naught, right? So C naught controls on 1 and targets on 0, and this is the circuit. So let's see, right? And now let's have a circuit which encodes the message. So now we assume that Alice has the first qubit, and based on the message, she can apply an operation to her share of the qubit. So this function is more generic. It takes this qubit as a parameter. And here the thing is that, so Alice applies an X if if the second bit of the message is 1, and she applies a Z if the first bit of the message is 1. Right, so both are applied if both are 1. So here, let's run this, let's basically define this function. And the decoder part here, what Bob needs to do is that Bob needs to apply an unentangling operation, which means that he applies a C naught, right, which unentangles it, and then he applies a Hadamard. So let's create this bell pair using the create bell pair function. Then we'll add a barrier. And after this, we are trying to encode this message, which is 1 0, right? We'll call the encode message function. And after Bob has received the message, he'll call the decode message function. So here we are assuming that it's the first qubit which Alice has access to. And then finally, they are going to measure all, and let's see what the circuit is going to be now. Right, so this is basically the entangled circuit, and after this we want to send 1 0. So Alice applies a Z, just a Z, and then in order to unentangle, Bob applies a C naught followed by a Hadamard, and then they are able to recover the messages. So here Bob is able to apply the C naught because Alice has already sent one pair of qubit. Right. So there's a question I see in the chat. Okay.
Yeah, I can read for you. That's
Yeah.
So
Sure.
Modeep is asking how many maximum number of control gates can there be in a gate in Qiskit, and Onnesha is asking how will Bob know which gate to apply to decode the information.
Okay. So the thing is that okay, so there are two questions. So firstly, how many control gates can there be in a gate in Qiskit? So the thing is that a gate is a single gate only. If you meant that how many control gates can be there in a circuit, in a quantum circuit, then of course, that depends on how much error and sort of circuit depth you can tolerate. So typically, if you have too many control gates in the circuit, it will contribute to error. Yeah, but I don't know if I got your question correct, because so one gate is one gate only, right? So you can't have more control gates inside a single gate. What you can think of is number of gates in a circuit, number of control gates in a circuit, and that depends on the noise profile. Okay, so these Jupyter notebooks are taken from Qiskit textbook. I'll send the link to those. How will Bob know which gate to apply to decode the information, right? So for Bob, the gates are not dependent on the message. So for Bob, it's always the unentangling operation followed by the Hadamard. It's on Alice, based on the message she is sending, the gates which she is applying, right? So Bob never applies gate based on the message. Bob has a fixed set of gates to apply, which is C naught followed by Hadamard, and then he recovers the state in the form of basis state. So he recovers the message in the form of basis states. Yeah. So this is the final circuit we are getting, right? And let's see if we run this, what happens, right? So we get actually 1 0 with probability 1, right? Because we actually we used this AER simulator, right? And here basically we get the results, and the results we see that there is a count of out of 1024 gave the measurement outcome as 10. So here there is actually no error, and we are able to send the message with a 100% chance. And if we want, let's also see what happens on real device, right? So right now we are assuming everything is perfect, but in the next couple of days we will also see noisy circuits, right? But although I won't discuss too much of noise over here, but the idea is that when you have noisy circuits, their accuracy can actually go down. So this probably I'm not going to run today, but the thing is that in real devices, your outcome may not be perfect and there might be some errors. In the next couple of days, we'll learn more about the noisy circuits part. If there are any questions about this implementation of super dense coding, let me know before I move on to density matrix.
No, there are no more questions yet.
Okay. Okay, so basically, as Shesha explained, when we have a mixture of states, we actually need a sort of a different sort of representation, which is called as the density matrix. The density matrix for, like, if you have some pure state, you can just compute the outer product as ket psi bra psi, and that gives you the density, corresponding density matrix. So let's take an example of this EPR pair. So this EPR pair consists of 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 1. So here we can actually just have this sort of a vector. This is indexed, the indices of these are 0 0 0 1 1 0 and 1 1. So basically there is a 1 position at 0 0 and 1 1 index. And now if you compute ket psi bra psi, you will actually have to just take the matrix multiplication of this column vector with this sort of a row vector, and what you get is half times this matrix, right? This 4 cross 4 matrix, and there is a 1 at each of the 4 corners. All the remaining entries are zeros, right? So okay, I think I'll have to change the kernel. Yeah. Okay. The thing is that now, so let's first create the CPR pair. So I apply a hard mod, I applied a controlled NOT, and then let's draw this sort of circuit. Right? So let's see how the psi AB looks like. So the psi AB is just 1 by root 2 0 0 plus 1 by root 2 1 1, right? So here 1 by root 2 is also root 2 by 2. And now the thing is that let's use the same circuit QC underscore AB to now compute density matrix. So for that we use this quantum information module. So we use quantum information dot density matrix dot from instruction QC AB. So QC AB is the circuit. And let's see the density matrix we obtain, right? So this is also what we just computed now. Right. And in order to visualize the density matrix, so there are actually, now you can see that it's a 2D sort of a matrix. So it's best to visualize it using the cityscape plot in Qiskit. So it's plot state city row AB dot data. And then I can see that on the 4 corners, I have this value of half, and the remaining entries are all 0. Right, so this is the real part and this is the imaginary part. So here the imaginary part consists of all zeros. And now actually the main motivation for these sort of density matrices was this idea of mixed states, right? So you can, instead of having one pure state, you can have a mixture of several such states. And the thing is that here the idea is that suppose if you have this sort of an EPR pair, right? Now the thing is that what is, if somebody asks, what is the state of Alice's qubit, right? So Alice's qubit cannot be described unless I have the full state. But the idea is that, one way to describe it is to assume that suppose if Bob would have made a measurement, right? So suppose if Bob would have made a measurement, and the state on Alice's side would have collapsed to either 0 with probability half, or it would have been 1 with probability half. Right? So it's a mixture of sort of this ket 0 and ket 1 state. And we actually now we represent it as the density matrix, which is half ket 0 bra 0 plus half ket 1 bra 1, which happens to be this half of I by 2 matrix, the identity by 2 matrix. we can construct even a more complex example. So I can have a state which is ket plus with probability um, mm, with probability 80%. So this is the ideal state which I wanted to prepare, but with 20% of the times the state can either go to one of the psi2 or psi3 states with 10% each. So overall, if I want to construct this density matrix, it will consist of 4 by 5 ket psi1 bra psi1 plus 1/10 ket psi2 bra psi2 plus 1/10 ket psi3 bra psi3. So this is how overall my density matrix is going to look like. And now if I want to compute this matrix, it will turn out to be this. But let's try to compute it using sort of this. So let's try to create it using NumPy. We create this sort of same matrix and then we import it in the QI, quantum information sort of thing. Right? So here you can see that sorry, yeah.
Yeah, if I may, sorry, just telling you. So there is one question by Swati. She is asking what exactly the imaginary part represents in density matrix representation.
So imaginary part on
What exactly the imaginary part represents in density matrix representation.
see, basically these matrices are all complex matrices, right? So rho is actually a Hermitian matrix, but non-diagonal entries can still be complex. Okay. Now the complex entries will have the real part and the imaginary parts. And since you can actually only plot one at a time, so they have plotted these two parts separately. Now, imaginary part by itself does not have a physical significance. It's just the total value which has the physical significance. However, one thing is that the diagonal entries here will always be real because it's a Hermitian matrix. Okay, any other question?
No, you can continue.
Yeah. So let's also discuss this unitary evolution. So if I have rho and I apply unitary, I actually get u rho, u dagger, right? So in Qiskit, you can use this dot evolve operation. So let's first, create a density matrix which consists of, state ket1 with probability 1/3 and with probability 2/3, it's the state ket plus. So you can actually do density matrix dot from label. So these 1 and plus, these are some of the fixed labels. And now we can draw this sort of a matrix which consists of 1/3, 2/3, and then 1/3, 1/3 are the non-diagonal entries. Now we can define our operator in a similar way, but now we use the matrix operator class. So the thing is that in order to define the operator, so we consider this y operator, the y polygate, which consists of 0, iota, minus iota, 0. And now we evolve our mixed state using the density matrix dot evolve operation. Right. So here we use rho 0, which we had constructed over here, and then we call dot evolve y. So this is the rho 0 p we get. Yeah, so okay, so this reduced density matrices and all we are not going to do today. But one thing I can just tell you is that you can also represent, these mixed states which we have just discussed. These can also be represented on the block sphere. And here it can be shown that if you want to represent a mixed state, like for a density matrix rho, you can actually always decompose it as half of I plus Rx poly X, Ry poly Y, Rz poly Z, where these are Rx. So basically Rz, Rx, Ry, Rz are coefficients. And the thing is that it will end up mapping to one of the points inside or on the surface of block sphere. So it can lie inside also now. Earlier, when we were talking about pure states, it always lied on the surface. And for pure states, it will turn out to be the same representation as we had discussed earlier. Yeah, so actually these examples are on partial traces, and also those probably I will not go into too much detail. Yeah, but let me actually just show you how rho h will map over here. right? So for us, okay, uh, yeah, so let's see what this row H we defined. So here actually they defined this row H. So you can also use this plot block multi-vector to plot this row H, and you can see that it almost lies on the x-axis, but it's not on the surface, it's on the inside of the sphere, right? And so basically its length is slightly smaller than that, right? Because it's not a pure state. Okay. Yeah, so actually that's it from my side. If you have questions, you can let me know. Okay, so yeah, so these notebooks are there, on Qiskit textbook page. Okay, so from there you will be able to get the notebooks. I'll give you the corresponding links. But yeah, if it was a bit fast, I can go over some of the parts again, like if you want. Yeah, actually I went too fast. Maybe yeah, it's only half an hour. Hmm.
Okay, so everyone, as Dhiraj said, that if you think there is some parts that would help if he repeats, please let us know now. Okay, Oyon is asking that,
Mixed
yes,
state.
yes, two of
Yes,
them are
Rajat
having the
is
same
also saying
problem.
mixed states. Yeah. Let me go over these then. So I have some trouble with understanding pure and mixed states. Okay, yeah, a lot of people are asking that. So the idea is that, like in terms of theory, the thing is that when your state is actually just, like typically, so the thing is that there is a notion of a quantum state, which is the state ket psi, right, which we represent by a vector. Now the thing is that you can actually have a sort of a classical mixture of multiple states, like an ensemble of several states. Here the thing is that when you talk about a quantum state, it's a sort of a coherent superposition between the possible states, right? The possible basis states. But here it's still a single state, right? Unless I make a measurement, it's still a single state. When we say we have a mixed states, it's like a probabilistic mixture of multiple such states. So you might say that, even a single state can be in a superposition of basis states, right? But that superposition is different from a classical mixture. When we have a classical mixture, then it's either this or this, right? In case of superposition, the thing is that, what I have is that it's in a sort of a state, and then if I make a measurement, it will collapse to one of them. It will also depend on which basis I'm making the measurements, but still it's a single state. When we say it's a mixed states, it's a sort of a classical sort of an ensemble of multiple pure states, right? And that classical ensemble, a representation for that is given by the density matrix. The density matrix was what Shesha had explained. The concept of this density matrix can be explained, the idea comes from this idea of outer product. So for a single state ket psi, we can compute its outer product set ket psi bra psi. When I take a bra psi, it corresponds to taking a conjugate of that column vector, which gives me a row vector. And if I take this sort of a product, I'm going to get this matrix. This is called as the density matrix. So here in these Qiskit cells, we just created this EPR pair. In order to create an EPR pair, we apply a Hadamard and then we do a controlled X, and then we get this sort of a circuit. And we can actually get a state vector from this circuit operation QC underscore AB. This is how what get psi AB was. Now coming to the density matrix part, the density matrix can also be computed from the same circuit using this density matrix dot from instruction operation. And once we get this rho AB, we can actually draw this thing. We'll get this 4x4 matrix. And in order to visualize it better, we were looking at the state city plot. Right. Now coming to mixed states. In case of mixed states, what can happen is that uh, the thing is that I can have, say, let's consider an example wherein I have a state which is with probability half it is get 0 and with probability half it is get 1. So here, if I compute this sum over I, Pi, Psi, Psi, which Shesha was explaining, I'm going to get I over 2, which is half times this identity matrix. Right. Now, similarly, I can even discuss, more complex states, more difficult states. So here it's a state which with probability 80% is going to be in the state cat plus. And with probability 1/10 and 1/10, it will be slightly rotated form of cat plus. And this rotation can happen in either direction. This is the overall matrix I get. So I do 4/5 time cat psi 1 bra psi 1. You will have to do this linear algebraic computation plus 1/10 of cat psi 2 bra psi 2 plus 1/10 of cat psi 3 bra psi 3. If you do this sort of linear algebra, you're going to get this sort of a matrix rho H. And one can actually then, take this rho H and draw it, and this is what you'll get. So here actually we computed it through NumPy. Yeah, so this was the overall idea of mixed states. And if you want to do an evolution of that mixed state, the thing is that every state can evolve under this U, but overall the density matrix will evolve as U rho U tapper. And this density matrix is a sufficient description of whatever information you can obtain from that ensemble. In order to understand this in depth, I'll refer you to second chapter of Nielsen and Chuang's textbook. Yeah, I know that this part is a bit advanced for the beginners, and maybe in the coding part I have gone a bit fast because actually see the coding functions don't have much, so it's just the library call. But the concepts which you have gotten in the theory session, they are the main things. And in order to refresh them or understand them better, you can also look at Nielsen and Chang textbook. The question over here is that how can I write bra or cat state in matrix form? So the thing is that means the coding part I need. So the thing is that in matrix form, these are like column vectors and row vectors. In terms of coding, if you are representing them through NumPy array, you can just represent the way you typically represent column and row vectors in NumPy. As far as the Qiskit is concerned, in Qiskit, your state is actually just a sort of a quantum state register, but it won't actually, the bra and psi are just the mathematical representations. So bra is just the adjoint of the kit. So there is a difference in the actual state and the mathematical representation. So the actual state is typically represented in the cat form only. The bra is taken for mathematical convenience, for example, in order to compute density matrix.
Okay, and Shomodip is asking, can we simulate open quantum systems in Qiskit?
You can simulate noise, but I don't know if so. The one thing is, of course, you can do is that if you this question might be too advanced for other audience, but what you can have is that you can consider more qubits and you can take few of those qubits as a system and the remaining as the environment, and then you can simulate whatever is the dynamics which is happening between system and environment. If you want to actually do it in that open or closed system framework. The other is that noise modeling is there in Qiskit. There are several libraries which you will find which can just simulate noise for you, or you can even run on the real hardware which has the real noise.
Shomodip is saying the Hamiltonian would become non-Hermitian.
We didn't discuss Hamiltonians today, but yeah, Hamiltonian is always a Hermitian matrix. Yeah, no, it won't become non-Hermitian. For open systems. Okay. Yeah, so for open systems, the dynamics are different, right? So for open systems, if you consider the total Hamiltonian of system and environment, that will be Hermitian. For representing its action just on the system, yeah, it will actually, I don't know if you can actually represent it, in the same Schrödinger's picture, because you'll actually need to take a partial trace. You'll need to trace out the environment and just consider system. So those things we haven't discussed in detail. Yeah, but yeah, you are asking good questions, but yeah, these are a bit advanced for the entire audience. Yeah.
Also, I hope just a comment on my portion that some of these will actually be cleared on Thursday when we have actually a lecture on noisy quantum systems, followed by a hands-on on how you can simulate those noise in Qiskit.
Okay, so let's stop for today if there are no further questions.
Yes. Okay.
Okay.
Devasmita, do you want to take over?
Thank you so much, Dhiraj, for this wonderful session. And we have already shared the attendance link in the
Yeah, so
chat.
I think students are also asking these links now from the Qiskit textbook, so I'll give them those.
Actually, yes, you shared the links, and during registration, we have already shared the Qiskit textbook links, which was a prerequisite for these talks. So I think everyone have the links of Qiskit textbook, but yes, for the particular chapter, they have to go through it.
Yes. Yeah, I'll share those.
So I think that's all. Is there any more questions from anyone else, or we can? There's few more minutes left actually. So, is there anything else to